Welcome back. Let's take a look at number 13 in our review packet. Calculate the density of an object that has a mass of 38.45 grams and occupies a volume of 24.7 cubic centimeters. Well, in case you have forgotten the formula for density, that's okay, because page 3 of our reference tables lists all of the formulas that we need for chemistry, and density is the first formula. Density equals mass divided by volume. So D equals M over V. I don't know why I wrote a 4. Going a little crazy tonight. All right. So let's plug in our M and our V. 38.45 divided by 24.7. I'm going to keep my units, so grams over cubic centimeters. If I plug this into the calculator, 38.45 divided by 24.7, I get 1.556680162. Whew, that's a mouthful. Fortunately, we don't need all of those numbers. We look at our sig figs. There's 1, 2, 3, 4 sig figs in our mass, 1, 2, 3 sig figs in our volume. The rule for division is to keep the smallest number of sig figs in the number. So we're not looking at the decimal, we're looking at the whole number, which means 3 sig figs coming from the volume. So 1.55, this is where we're going to chop it off to round. This 6 tells us to round up, so 1.56 grams per cubic centimeter. And if you were asked to go the extra step and identify the object with those particular properties, you could go to our reference tables in our front section, and you could look up densities that are similar to it. If it told you it was a metal and our density was 1.55, well, none of these are a very good match. The closest one looks to be magnesium at 1.74 grams per cubic centimeter. Perhaps it tells you, though, that it's an organic substance. 1.56 is very close to 1.54 grams per cubic centimeter. So, barring some slight experimental error, this could be glucose. C6H12O6, the sugar that's in our blood. It was a gas. We could go down here and find out that hydrogen sulfide has a density of 1.45 grams per, whoops, that was grams per liter, not grams per milliliter, so we'd have to do some conversions. None of these would be a very particularly good match. But again, they would have to tell you what kind of substance it is we're looking at, and this problem does not do that. All right, number 14 we can do on this video as well. Identify the following as a physical or a chemical property. So remember, physical property is a property which can be observed without changing the identity of the substance, whereas a chemical property actually changes the identity because it makes a chemical change happen. So the fact that you are a liquid at room temperature, that is phase or state conditions. That is a physical property. You can observe water, for example, my glass of water is a liquid, and making this observation does not require me to destroy the water in any way. All right, surface tension. That is a physical property that I can observe and measure, perhaps, without actually destroying the sample. So water has a particular surface tension value. Different substances have different surface tensions. We can measure it without actually reacting anything. Density, physical. Okay, you can measure density without destroying the substance. Boiling, physical. You might be tempted because there's a lot of energy change happening. It's absorbing a lot of energy to say that it's chemical, but you can undo it. So if I boil something, for example, liquid water, it makes steam, gaseous water. If I condense the gaseous water, I can get my liquid water back. Okay? It's not just that it's reversible, it's that the identity of the substance in question was always H2O. It doesn't matter what state it's in. It's always the same chemical. So, physical. Reacts with an acid to produce hydrogen gas. You don't even have to read anything after the word reacts, because reacts makes it chemical. Electrically conductive. Physical. Okay? Copper wire does not change substances, does not change identities, just because you run electric current through. Dissolves ionic compounds. Okay? This one's actually a little complicated going on, chemically speaking, but just look at the word dissolves. This is a physical process. Think of salt water. I can dissolve salt into water, and it would be indistinguishable from the original water. However, if I boil away the water, I can reverse this and get my substances back. I will have solid salt, and I could collect the water as a gas and condense it back into a liquid if I were so inclined, but the point is you can separate the two substances out from each other. There was no chemical change, therefore it is a physical property. Breaks down into hydrogen and oxygen gas. Well, breaking down is like reacting, and so this is a chemical process. The one that I accidentally crossed out, color, can be observed without altering it, physical, and inert, meaning it does not react, chemical. Okay? Let's go ahead and do the next couple down here. Draw and label a picture of a water molecule and explain why it is a polar molecule. Well, water is H2O. We can draw a Lewis structure for it, and strictly speaking, you could draw the Lewis structure like so, but we can use Vesper theory to make a slightly more appealing Lewis structure, which shows off water's bent nature, with its two lone pairs sharing that side. And to explain its polarity, we have to remember a property called electronegativity. How much an atom attracts electrons to itself in a bond. Well, we have hydrogen all the way over to the left, and oxygen pretty far off to the right. Electronegativity, as it turns out, increases going diagonally up the periodic table until you hit the noble gases, and then it just drops off to zero because, of course, noble gases don't bond, so they can't attract electrons in a bond. Makes sense? All right. So looking at the hydrogen-oxygen bond, oxygen is much more electronegative than hydrogen. And so in both of these cases, it is going to attract electrons towards itself in this bond. Since the electron density is going up around oxygen, it will have a partially negative charge, and the hydrogens will acquire partially positive charges. This is the dipole of water. The dipole points towards the oxygen in this particular molecular structure. And having a dipole makes it, by definition, a polar molecule. What does table salt why does table salt, NaCl, dissolve in water, but not in cooking oil? The key here is a little phrase called like dissolves like. But a little explanation is necessitated. Table salt is an ionic compound, meaning NaCl is just the formula unit for the crystal, and there are sodium ions and there are chloride ions in a crystal lattice. You put it into water, and water, with its polar structure, with a partially negative charge on the oxygen, will attract the fully positive sodium ions, while the partially positive hydrogens will attract the fully negative chloride ions. This rips apart the crystal, separating it into its constituent ions. This is dissociation or ionization, and it dissolves in the water. Cooking oil, well, I can't give a chemical formula because oils are a group of compounds with lots and lots of formulas, but an example of an organic structure of a cooking oil would be a bunch of carbon-carbon bonds, and everywhere a carbon doesn't have 4 bonds, it would have hydrogens hanging off. These are very non-polar, okay? Whereas water is polar. Since there's no charges, no dipoles that are pretty prevalent in this non-polar molecule, it can't pull apart the sodium chloride crystal because it relies on electric attraction. You don't have that going on in cooking oil. Or we can just summarize this in 3 words: like dissolves like. And quick definitions for number 17. I don't want this video to get too long. Solute. Pen stopped writing. Here we go. Solute is what dissolves. It occurs in the lesser quantity. The solvent does the dissolving. It occurs in the majority. So most of the solution is composed of the solvent. The lesser part, the minority, is composed of the solute. And the last word, solution, is a homogeneous mixture. Any homogeneous mixture, in fact, consisting of a solute and a solvent. It could be a liquid solution, a gaseous solution, or even a solid solution, for example, brass or stainless steel or sterling silver, all of which are metal alloys. Tune in for the next video for the next set of solutions.